Hello and welcome to REMCOM's webinar on simulation of massive MIMO beamforming in an urban small cell. I'm Greg Skidmore, the director of REMCOM's Propagation Software Tools group, and today I'm going to be presenting the results of some work that I did with a colleague, Dr. Gary Bedrosian, looking at massive MIMO and evaluating its performance in a small cell. The reason we began this study was because MIMO, including massive MIMO, is a key technology for future 5G systems. Our objectives for the webinar were to use Wireless InSite's MIMO capability, released last fall, to predict channel characteristics for massive MIMO systems in an urban cell, including evaluation of multiple beamforming techniques using the outputs from the simulations. Our agenda involves first covering some of the basic concepts for MIMO and beamforming, then walking through some of the steps for simulating MIMO and Wireless InSite, then the techniques that we use to apply beamforming to the simulated channel matrix outputs from the Wireless InSite simulations, and finally showing some of the results, visualizing beamforming and looking at signal interference plus noise ratios and other outputs from the simulations. We expect this webinar to take approximately 30 minutes, plus questions and answers. You can ask questions at any time during the webinar using the panel shown in the diagram in the webinar screen. In addition, you can optionally undock the question panel and pull it out and expand it to make it easier to enter your questions. We'll have staff online that may answer some of the questions during the webinar, and we'll hold an open question and answer period at the end. So massive MIMO provides a number of benefits for 5G. Some of the major objectives for 5G are shown on the left in red: 1,000 times mobile data volume per area, 10 to 100 times data rates, 10 to 100 times more devices connected wirelessly, 5 times lower latency between devices, 100 times energy efficiency, and longer battery life for lower power devices. So when we look at massive MIMO to see how it addresses some of these, you can see that there are estimates that massive MIMO provides about a 10 times increase in capacity and throughput through spatial multiplexing. It allows for tens of devices, 10 times or more in each frequency band. It provides a significant reduction to latency by eliminating multipath fading. It allows for much more efficient use of energy and spectrum by directing the signal to each user. Estimates are that this can provide approximately 100 times efficiency. And because it's directing beams to individual users rather than transmitting over an entire small cell indiscriminately, it can use inexpensive, low-power components. So massive MIMO beamforming uses a large number of transmitting antennas to send focused beams toward individual users. And this allows a base station to send simultaneous data streams to many users within the same small cell, within the same frequency band at the same time. To do this, the base station receives pilot signals from each of the devices in the scene and uses those to characterize the channel between the base station and the devices. It then sends different signals to different users over the same frequency by forming individual beams to each of the users. This shared frequency increases the capacity and the data rate overall. On the bottom left, we show a diagram of how this kind of beamforming is often conceptualized. So the base station with its large array of antennas can form very narrow beams to individual devices. But the reality is that in an urban small cell, with all of the multipath and reflections and diffractions off of buildings, there may be a much more complex beam. And on the bottom right, we show an example of beamforming from 128 transmitting elements from a base station shown in green to a device shown in red. And this is using a technique that also tries to minimize interference to these other devices, shown as red circles. We can see that in this case, the beams are bouncing off of buildings, and there are actually multiple beams being sent in and around and through the multipath. So clearly, beamforming can be quite complex compared to a simple narrow beam diagram. To simulate MIMO, one technique is to use three-dimensional ray tracing. In Wireless InSite, this is the technique we use. 3D ray tracing provides a great deal of information about multipath. If we look to the diagram to the right, we can see individual paths, some of the strongest paths between a transmitter and a receiver moving along a route. These paths then translate into what's called the complex impulse response, shown at the bottom right, which shows the arrival of copies of the signal as a function of time. So 3D ray tracing can capture this level of detail. It can provide the complex path gain, sometimes known as the complex channel matrix. It can provide detailed 3D path data with all of this information about the time and also the phase information between all of the elements of the antennas at the transmitter and the receiver, the angles of arrival, the polarization, and all the other details that are critical to understanding the multipath in the scene. And perhaps most importantly, a solution that uses ray tracing can ensure that as something moves through a scene, you get spatial consistency from point to point, something that a statistical technique would not be able to capture. The fact that the paths may not change very much over a local area, but then can change dramatically over the full course of a route. The problem with the 3D ray tracing solution out of the box is that this problem can be very complex, particularly if you have a massive MIMO system that may have hundreds of elements in its array. Traditionally in ray tracing, every new transmitter is a new simulation. So as an example, a massive MIMO antenna with 128 antennas, elements, would require 128 simulations. So one of the things that the Wireless InSite MIMO capability has been developed to handle is to deal with this potential for a large increase in simulations. We've included a number of optimizations that help to overcome this. To start with, we use our GPU-accelerated and multi-threaded X3D ray model, and then we incorporate two additional key optimizations. The first is something called adjacent path generation that calculates path data in detail for a coarse set of data and then adjusts it to the MIMO antenna positions. And we have an additional MIMO optimization that then quickly finds the precise paths to the elements of the array. The key here is that we keep track of all of the path data. We adjust paths including all of the reflections and diffractions in the scene. And we manage all of this data and capture it for all of the pairs of antennas at the transmitting and receiving elements of the MIMO system. With these optimizations, we're able to do this while minimizing how much additional calculation time is required to perform the simulations. And those optimizations were critical for the massive MIMO simulations that we're going to show in this webinar. So once we calculated the complex channel matrix, we applied two different beamforming techniques to evaluate how beamforming would perform in our urban environment. The first technique is called maximum ratio transmission, or MRT. This sets the beamforming weights for the elements of the array to maximize the sum of all the channel gains to an intended device. On the diagram at the right, the intended device is shown in red, and other neighboring user equipment or devices are shown in blue. And as shown in this beam, there's no attempt made to minimize interference to these other devices. If they happen to be in the beam, then they'll have strong interference as well. The second technique is called zero forcing. In this technique, the beamforming attempts to minimize the interference to all of the users in the cell, placing them within local nulls. So if we look at the bottom of the screen, bottom right, we can see the same case, the same positions of an intended device in red and two neighboring devices in blue. And in this case, the neighboring devices have been placed into a null in the beam so that they don't receive very much interference. For this study, we developed some analytical tools and applied them to the simulation results. And these tools are essentially a preview of future capabilities that are planned in the roadmap for Wireless InSite. So in this diagram we show we have the inputs to the scenario, the antenna array, the urban geometry. We perform Wireless InSite simulations. These generate what's known as a complex channel matrix, and then we performed beamforming post-processing on these to calculate beamforming weights and calculate the beams, the power, and the signal interference plus noise for all of our devices in our scene. So next, if we look at our small cell scene, what I'm showing now is Wireless InSite in this view of this scenario in Roslyn, Virginia, an urban small cell in which we've placed 16 devices, one of them moving along a mobile route down a street and around a corner. We have also placed a base station, a massive MIMO base station in the bottom middle. If we zoom in on this, we can see that this base station is actually an array of 8x8 array of antenna elements, and it actually has cross-pole elements as well, making a total of 128 elements between the vertically and horizontally polarized copies of the antenna. Wireless InSite provides some simple techniques once we've set up a scene like this to set up our array antenna. We can simply create a new antenna. And then we use an antenna array builder for the MIMO antenna. Now in this case, we will choose to create a half-wave dipole and create an array of these dipoles just to show how we went about creating our antenna for this simulation. So Wireless InSite does not restrict anything about how the antennas in the array can be placed. They can be in non-uniform positions, but it does provide a simple mechanism that allows us to quickly build up an array. So in this case, we will select the ability to place our wavelengths as a function of spacing, our antennas, I mean. We place each of the antennas with a spacing of half a wavelength, and to replicate what we did in our simulations, we will create an 8x8 array. And now we can see that we have now created an array of vertical dipoles at each of these 64 positions. Now in the case of our simulation, we also wanted to have another 64 cross-polarized elements. So we bring up our MIMO array builder again, and we can go through the same steps to create our horizontal elements. The one difference this time is that we notice that our array is facing down the x-axis of this coordinate system, so we want to rotate the antenna. And now we can see we've got a horizontally polarized dipole antenna pattern, and we've added this to our array as well. So we now have 64 elements that are vertically polarized as before, and we have another 64 elements in the same positions that are horizontally polarized. In an actual system, we might have patch antennas or some other type of antenna type that achieves this same goal. So once we've created the antenna, we can then perform simulations. In this case, we set our antenna to have a frequency, our system to have a frequency of 28 gigahertz, and we created this massive MIMO array. One of the first things we then wanted to do was look at how the beams, how the fields propagated through our system. So we placed a field map of 64,000 receivers, and we calculated the fields on this field map as a backdrop to understand how the fields propagate in our scene. Now we can see here that from this base station we get a lot of energy that propagates down the street directly in front of the array, and we also get strong fields propagating to the sides. And what this first field map represents is the fields that we would get from a single dipole antenna before we apply any of the beamforming techniques to our array. So these are the initial propagating fields from each of our dipoles, and this is the starting point that we can then use to try to direct beams to all of our users in this cell. If we follow the route that's propagating through this cell, we can plot the power, the received power along this route. And here we can see that the power increased up to a position here near the peak, which was about the point where the corner right in front of the array, and then it began to drop again as it drove down the street and then drop off as it passed around the corner at the end of the street. One of the other things that we see here as well is a lot of multipath fading, the peaks and nulls that we see as the device is moving along. And this is caused by constructive and destructive interference between all of the paths in our simulation. So when we then simulated this with the full MIMO array and plotted this received power for each of our 128 transmitting elements to this device as it moved along the street, we see a lot of variation, even though these antennas were only half a wavelength apart, which at this frequency is spreading over just a few centimeters from side to side and top to bottom. We see a great deal of variation in the multipath, and although there is similar fading going on, the peaks and nulls are happening at different places on these different elements of the array. And this variation is precisely what Massive MIMO and MIMO in general can take advantage of to try to direct beams and optimize how the energy is sent to the individual devices in the scene. Now we also see a general trend here of some higher peaks and some lower values. The device moving down the street had a vertically polarized antenna, so in general the received power to this device from all of the horizontally polarized elements was much lower than it was from all of the vertically polarized elements of our array. So next, if we want to look at some of the beamforming, we've chosen two devices, two positions along our route that we want to look at the beams to. The first one is shown in a large red dot here, and then as the device continued along the route and around the corner, we have a second position shown in the red dot in the middle of the screen here. So the first position was the 20th point along the route, and when we applied our beamforming techniques, we can see a slight shift in how the power is being directed. This isn't a perfect singular beam. We actually have some different lobes. A very strong lobe is reflecting off the side of a building and making its way to our receiver point. There's another lobe that is coming along from the side, along the side of this blocking building. And there are also other side lobes that go down other streets and down the main street in front of the array. But we can clearly see quite a change over the previous field map showing how the energy has been redirected toward this device. If we then, so this is showing the maximum ratio transmission technique, the one that tends to maximize the power to our device without respect to any other devices. If we then look at the beam to the second device position, we can clearly see that the beamforming has now moved the beam to shoot directly down in front of the array. It's a very strong beam, and again, this is using maximum ratio transmission. It's directing a very strong beam toward our intended device, and it's not considering it in any way the other devices in the scene and whether this is generating interference toward them or not. Now, the second technique that we looked at was called zero forcing. Looking at these same two positions again, first we have our first beam, and again we can see that it's taking advantage of this strong reflection off the side of the building and some diffraction around this the side of this obstructing building to get a strong signal to our device. However, we notice a slight difference this time. If you look closely, you'll see that each of the other devices happens to be sitting within a null in the pattern. And so our technique has made an attempt, the zero forcing technique has made an attempt to try to minimize the interference to all of the other devices. The beam to our intended device is not quite as strong, but the interference to the other devices has been significantly reduced. If we look at our second position along the route, we now see a much more intricate beam pattern that was formed to try to get to the second position. Because there are several other devices blocking and beyond this device straight down the street, the zero forcing technique has actually created some beams. There's a small beam that heads straight toward the device, but some of the strongest beams are actually reflecting off the buildings to the left and to the right. And again, as we look around the scene at the other devices, the stationary devices in the scene, we'll see that they are in individual nulls that have been created by the zero forcing technique to try to minimize interference to each of those devices. Next, if we look at an animation of how these beams changed along the full length of this route, we can watch how each of these techniques performs as the device is moving. So as before, we see the strong beam following our device in red that's moving along the route. And as this beam follows it, there's no attempts to minimize the null, so you see it sweep across all of the other devices, and whenever our intended device moves in front of them, they receive interference. Next, if we look at the zero forcing technique, we see a similar set of changes occurring. However, we see the pattern very carefully shifting in ways that is continually keeping nulls on our other devices. The beam down this main street with several other devices is clearly not quite as strong as it was for the maximum ratio transmission, but the technique is continually keeping the other devices in a null and minimizing their interference. So next, if we want to evaluate how this performance how each of these techniques has performed in terms of another metric, the signal to interference plus noise ratio is a key measure for determining the quality of the signal that's being received. So not just the signal power, which is in the numerator, but also the interference and the noise are a key part of the signal interference plus noise ratio. In our case, the interference is the total power from all of the beams that we have formed with this beamforming to the other devices. So in the previous animation, we showed the beams to our intended device. At the same time, we calculated the beams to all of the other 16 devices in the scene. And for each case, if we have a device such as this second device here with the pink beam, and the first device is caught in that beam, that becomes interference to this device. And so our signal divided by the interference is the ratio of this intended beam in green to the interference in red. In addition to interference, we used RF background noise based on some literature, and we assumed approximately a negative 87 dBm of noise based on an assumed 100 megahertz bandwidth and ambient noise levels that have been measured in some of the literature at these frequencies. So we look first at the received power along the route. We see the maximum ratio transmission in blue and the zero forcing technique in red. And we can see that over most of the route, maximum ratio transmission has delivered more power to our intended device, other than the areas directly right in front of the array. Overall, this was about a 13 dB improvement, or 14 dB improvement over the zero forcing technique. When we look at the signal to interference plus noise ratio, however, we see a very different picture. Again, we have the maximum ratio transmission in blue, and we have zero forcing in red. The zero level, when the intended beam and the interference are equal to each other, is shown right along the line here. And we can see that for the maximum ratio transmission, even though it had higher power, there were many places where its signal to noise level actually dropped below zero. And this was due to the fact that it was interfering. The beams to the other devices ended up interfering in many cases more than the power of the intended signal. Maximum ratio transmission has this issue, but zero forcing, on the other hand, was able to minimize the interference. And we see a signal to interference plus noise ratio here of 30 to 50 dB, and then eventually dropping down to about 10 dB until the device went around the corner, and at that point the zero forcing dropped very rapidly in its signal interference plus noise. So for this beamforming comparison, the bottom line is that the received power from MRT was about 14 dB higher than zero forcing, but because of the interference from the other beams and the fact that the interference was minimized by zero forcing, the zero forcing was able to deliver an average of about 25 dB higher signal to interference plus noise than MRT. Next, we looked at a special case called pilot contamination. Pilot contamination is an issue that beamforming can suffer because MIMO systems, particularly Massive MIMO, use pilot sequences from each of the devices to estimate the channel between the base station and the device. If we look at the diagram at the bottom, the pilot signals sent from a device are sent to an intended base station, shown by a blue arrow, But those same pilot signals will also reach neighboring base stations. And in some cases, the device in a neighboring cell may be using the same pilot sequence. When this happens, it's called pilot contamination. And the problem that occurs is that the base station receives the same pilot signal from both devices and thinks that they're essentially the same device. When it then forms its beam back to what it thinks is one device, it's actually diverting some of its energy accidentally to the second device and also degrading some of its calculations, reducing its beam to the intended device. So in our simulation, we created a device here shown in blue, which we used as a simulation of a device that was introducing pilot contamination. We assumed that this device was in a neighboring cell, perhaps a tower to the south or the northwest of the screen, and that it was sending the same pilot signal as the device that we had moving along our route. When we look at the received power under these conditions, we see a couple of interesting trends. First, the maximum ratio transmission changed from the dark blue line to the light blue. We see some slight changes, but over most of the route, there's actually very little change in the received power. And on average, it ended up being a mean of about 2 dB less power when there was pilot contamination. When we look at zero forcing, we see a slightly stronger effect, dropping from the red to the green. And overall on this route, this resulted in about a 6 dB loss in power. When we look at SINR, however, we see a much different effect. Again, we have the blue dropping to light blue for maximum ratio transmission. This was about a 2 dB loss in SINR. But for zero forcing, we dropped from the red line to the green line. And essentially what happened is, because this device moving along the route was suffering pilot contamination, our base station, in the beams that it formed to all of the other devices, was not able to successfully minimize the interference to our device. So while the power only dropped a little bit, the interference from the 15 other beams to other devices in this small cell was significantly higher. And this increase in interference dropped our SINR over the route. If we look at an overall summary of the results, the impact to MRT was about 2 dB to both the power and the SINR. And for zero forcing, it was about 6 dB loss in power, but an average of about a 29 dB loss in the SINR, greatly degrading the performance of this beamforming system. In addition, there was an increase of about 9 to 12 dB interference to that neighboring device caused by the base station, both by MRT and zero forcing, directing more energy into the device in the neighboring cell without realizing it. So the bottom line from this is that unmitigated, pilot contamination is a severe issue for beamforming, particularly massive MIMO beamforming. Fortunately, the research community knows this, and there's a lot of work going on to work on techniques to mitigate pilot contamination. So in systems that get deployed, it will likely be mitigated, but understanding that it's a problem and having tools to simulate the problem and mitigation techniques is a valuable tool for simulation. Now, another thing that we discussed was the built-in optimizations. As we mentioned earlier, these optimizations made this study possible because we were able to do the large field maps that we showed that allowed us to show beamforming in action. We ran some simulations and recorded them on a high-end desktop workstation, and we recorded the runtimes that we got in our simulations and compared them to what we would have gotten if we had taken our baseline simulation and had to run it 128 times, once for each transmitting antenna element. So before any optimizations, a single antenna at the transmitting base station and a single antenna at the device takes about 53 seconds to simulate all of the routes and points in our scene. When we applied the acceleration that we talked about called APG acceleration, this dropped to about 35 seconds. And when we then simulated our MIMO antenna with 128 elements, again to the route and the 16 devices in the scene, The total runtime was about 76 seconds for our MIMO simulation. If, on the other hand, we had simulated each individual antenna one at a time, the total runtime would have been about 113 minutes. So this was about 89 times faster. We also simulated a field map in the background with about 66,000 points. This field map was used to display the beams. It was not part of the calculations of SINR or received power, but it was used to display our beams on the map across the scene so that we could see what they looked like. So with these 66,000 points, our initial simulation took a little over 3 hours to complete. When we applied the APG acceleration, it completed in about 3 minutes. And when we then expanded from a single transmitting antenna to 128 antennas, it ran at about 37 minutes. And again, if we had taken our original 3-hour simulation and ran them one at a time, it would have run for about 16 days to complete. So we see a speed up here of about 600 times. This kind of speed up is important not just because it reduces the runtime, but because it allows an analyst to run several different conditions, change something, look at a case, run simulations again. So the speed up in runtime when we're talking about massive MIMO arrays is extremely important. So in conclusion, we've presented a new and efficient method for predicting detailed channel characteristics for massive MIMO using our new Wireless InSite MIMO capability. We simulated massive MIMO in a small cell, and we generated channel matrices from our simulations. We then used post-processing analysis to compute maximum ratio transmission and zero forcing beamforming, and we showed results from our calculations of power, interference, and SINR. In this particular case, zero forcing was much superior when there was good channel state information, but when we introduced pilot contamination, it had a severe effect on that performance. This study has demonstrated the MIMO capability, and it provides some insight not only into what MIMO beams look like in a complex urban setting with a lot of multipath, but it also shows the kinds of things that you can look at when you have a good MIMO simulation capability to help you assess beamforming solutions. Now I'd like to turn it over to questions. So first question, is the MIMO capability limited to large arrays for massive MIMO? And the answer is it's not. We can do any size of array. Smaller arrays will not see quite as much of a speed up if you had a 4-array antenna or an 8-array antenna. But there's no restriction on the size, the placement of the antennas, or how they are oriented. There's a question about where beamforming is implemented in Wireless InSite. The beamforming techniques are in our roadmap for future versions of Wireless InSite. For this study, we performed offline calculations. What we calculated in Wireless InSite was the complex channel matrix from the 128 elements of the transmitting array to all of the other devices in the scene. We then used this offline calculation to calculate all of the beamforming. And we have then put those results into versions you can view within the GUI. But at the present time, the beamforming has not yet been included in the GUI. Another question is whether the Wireless InSite simulation can handle frequencies below 6 gigahertz. So although we showed our simulation operating at 28 gigahertz, and Wireless InSite is valid up into millimeter wave frequencies, it is also valid down to below 6 gigahertz. It can be used for indoor and outdoor environments. And so it has broad use for all kinds of MIMO applications. And there was a specific question about small room setups. We also can handle small rooms in addition to outdoor and indoor in general, like an office floor plan. You can also set up a small room. You can place furniture. You can look at interactions with the furniture. And as in a previous webinar that we provided a few months back, you can include furniture and diffuse scattering from that furniture as well with the new diffuse scattering capability. There's a question about the beamforming techniques. As I mentioned earlier, we used offline calculations to look at zero forcing and maximum ratio transmission. Other techniques would be possible. These were just two that we used for this study. There are many other techniques, many of which fall between the maximum ratio transmission and zero forcing. So we use these as sort of some examples of two ends of the spectrum of maximizing power or minimizing interference. Many of the other techniques try to balance those two things. Thank you for joining us today. There are some other questions, and we will try to respond to these and get back to people who have attended later on in follow-up. In the meantime, I would encourage you to write down the number or the emails shown on the screen now, and please feel free to contact our sales team to talk more about the Wireless InSite capability and the MIMO capabilities. Thank you very much for joining us today.